Good morning everybody. Today we are going to discuss half adder and full adder topics from Digital Electronics and Computer Organization. I am Dr. Michael, Associate Professor, CSE Department, MLR Institute of Technology. So today we will be discussing the topics half adder, full adder, and we will use KMap to get a simplified expression for full adder. Also we will be discussing the applications of these adders. So first, introduction to half adder. Addition of 2 bits is nothing but half addition. For example, 1 bit can be represented by 0 or 1 in binary form. So 1 plus 1 or 0 plus 1 or 0 plus 0. Such combination is nothing but half addition. Now, the inputs for half addition, as I said, we add 2 bits, first bit A, second bit B, and the result can be, you know very well, since school days you have been studying addition. Whenever you do addition, you can get sum, you can get a carry. So the result is we can get a sum, we can get a carry. Next. Now what is half addition? As I told you, it is simply addition of 2 bits. It could be 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. These are all the possibilities that we can have. Now let us add 0 plus 0, you know very well, sum is 0 and then carry is 0. Now for the second case, 0 plus 1, sum is 1. Do we get a carry? No, the result itself is 1, so carry is again 0. Next case, 1 plus 0. 0 plus 1 is equal to 1 plus 0. Okay, so no issues. So we will get the same result as in previous case. Next, 1 plus 1. 1 plus 1 is in binary form. The sum we get is 0 and the carry we get is 1. Right? To understand this, let us take one small example. Suppose if we perform binary, okay, to understand the binary addition, let us perform decimal addition and then understand binary. Suppose if you want to do 9 plus 1 in decimal, then what we do? We get the result as, you know very well, 10. So what is 0? 0 is the sum, and what is 1? 1 is the carry. Right? Now 9 is the highest value in decimal. Decimal, you know the values are from 0 to 9, right? So 9 is the highest value in decimal number system. Likewise, in binary, the highest value is 1. Binary numbers, we have only 0 and 1. So the highest value is 1. So applying the same logic, 1 plus 1 in binary, okay, so 1 is again the highest, right? So 1 plus 1 should be equal to 1, 0, and that is the reason we get, okay, carry, we get carry as 1. Here it is indicated carry is 1, and then the sum we are getting 0, which is indicated here. Okay, I will expect students to remember this. When we go for full adder, we can use the same concept there. Right? So now next what we are going to do is we are going to identify the circuit for half adder. For that we have to go back to the table which we have just seen. Now here let us observe this table very carefully. This part of the table, if you see, this is nothing but the truth table of XOR gate. Okay, truth table of XOR gate. I hope all of you remember that this is the symbol of XOR gate. Okay, right? So truth table of XOR gate. What we got? The sum of half addition is same as the truth table of XOR gate. Okay, right? Next, let us observe first, second and only the carry column. So we are going to observe only this one, and then next this one. That is skipping the sum. Suppose we don't look at the sum. Now the A, B and carry, these three columns, they represent the truth table of AND gate. They represent the truth table of AND gate. So from this we can conclude that sum is nothing but XOR operation of A and B. Carry is nothing but AND operation of A and B. So that is the reason here sum is nothing but the XOR operation of A and B. Likewise, carry is nothing but the sum is nothing but the XOR operation of A and B. Carry is nothing but the AND operation of A and B. So in this manner, we are able to complete the circuit diagram of half adder. So this is the general process that we follow to achieve any digital logical implementation. So what is the process? First, we are looking at the functionality, and from the functionality we are achieving the table. So what are we doing here? Half addition is nothing but addition. So we are performing addition, we are getting the table, and from the table we are identifying what logical gate will perform this operation. Based on that we are finding out the circuit diagram. Okay. But the same simple technique may not be useful in all the cases. What do I mean by that is, just by looking at the table we may not be able to guess what logic gates are enough to implement this functionality. So we need some simplification, for which we use KMap. Okay, next let us see what are the limitations of half adder. Now first of all, why do we need half addition? Suppose, okay, you want to add say just 2 bits, 1 plus 1, okay, right, you need half adder, fine. But let us take one example, say 0 1 1 0 and then 0 0 say 1 1 addition. Now if we want to perform this addition, 0 plus 1 we will get 1, right. Next 1 plus 1 we will get 0, carry 1. But now here if you see, we need to add 3 bits, 1 1 0. This is the carry, okay, and half adder can only add 2 bits. It can perform 1 plus 0. But what about this one? So this is the limitation of your half adder. It cannot add carry bit. Then this is the major drawback of the half adder, and most of the real life situations, as I just mentioned, you need addition of 2 bits with carry, okay, which means you need addition of 3 bits. So most of the real time scenarios the half adder is not able to achieve. To overcome this issue, we go for the next one, full adder. By this time I hope all of you might have understood, full adder is nothing but addition of 3 bits, okay. Now if suppose we don't have this Cn, then it is same as half adder. Now because we have this Cn, right, it is performing full addition. What about the case when you have a carry? Yes, this is going to work. Hence this is called as full adder. So addition of not only just 2 single bits but also with carry. So it is addition of 3 bits. So obviously 3 inputs, and like in previous case, we can get output sum, we can get output carry. Now we'll follow the same process which we did previously. Now for 3 bits, the possible combination, you will get 2 power 3, which is 8. So these are the total 8 possible combinations which A, B and C in can take, right? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, 8 combinations. Now what we need to do here, same process as in previous case, 0 plus 0 plus 0, 0 plus 0 plus 0, you know very well, sum is 0, we are not getting any carry because result is also 0, carry is also 0, okay. Next case, second case, 0 plus 0 plus 1, sum is 1, of course we didn't get a carry, right, so carry is 0. Next, 0 plus 1 plus 0, you know very well, 0 plus 0 plus 1 or 0 plus 1 plus 0 should give the same result, so same as previous case. Next, 0 plus 1 plus 1, right? Previous case we have seen in half adder 1 plus 1, in half adder we have seen 1 plus 1, sum is 0, carry is 0. To that we are adding 0, means we are not adding anything, we are adding 0 means we are not adding anything, so the result should be same as previous case, what we got, okay, 0 1. Next, 1 plus 0 plus 0, 1 plus 0 plus 0 should be same as 0 plus 0 plus 1, correct? So we should get the same result as in this case, we should get the same result as in this case. Next, 1 plus 1 plus 0, next case 1 plus 1 plus 0, let us do 1 plus 1, 1 plus 1 already we did in half adder, we got this one 0 1, to that we are adding 0, we are not adding means adding 0 means adding nothing, right? So result should remain the same. Next, 1 plus 1 plus 0, next one 1 plus, next we are here 1 plus 1 plus 0, 1 plus 1, half addition we have seen, the result we are going to get this, to that we are adding nothing, so the answer will remain the same. Next, what about 1 plus 1 plus 1? Okay, that is one case, we will study that separately. 1 plus 1 plus 1, 1 plus 1 already we have seen, okay, that is 1 0, right, 1 plus 1 is 1 0, 1 0 plus 1, this is something like in your, this is now similar to decimal, 10 plus 1 is 11, the same answer you are going to get, okay, 1 0 plus 1 is 1 1, so sum will be 1, carry will be 1, last case, right. Next, now in half addition we could simply look at the two table, identify what gates and what circuit will perform half addition. Now coming to full adder, what we need to do here for the case of full adder is, we got a complicated table, we have got a complicated table. Now let us see, just by looking at the table can we identify the gates or the expression which will perform sum. Okay, let us start with sum. Now if you see, let me mark one portion of this table, okay, let us mark one portion of this table. Now if you see, this is nothing but your XOR gate, this is nothing but the two table of XOR gate, okay. Then now in XOR gate, right, if the result that you got, if you are doing XOR with 0, okay, then the value doesn't change. What do I mean by that? Let us go to the previous case. In XOR gate, let us analyze this. Now let us take these two cases where when you are doing XOR with 0. First case, when we did 0 XOR with 0, we have discussed that this is nothing but the XOR gate. Earlier we have discussed that. So 0 XOR 0 is 0, right? Then 1 XOR 0 is 1, means whatever the value we have here, the same value we got. Likewise, whatever the value we had here, the same value we got. Okay. So, based on that, what we can conclude here is sum is nothing but, so first from this particular table, sum is equal to B XOR Cin, but we cannot stop there. We also need to consider the other input, which is A, right? So, considering the other input A and just based on the theory that we discussed, this is nothing but, okay, the XOR of A, B and Cin, okay, right? So, we can conclude that sum is nothing but, we can write like this, okay, sum is nothing but A XOR, sum is nothing but, okay, A XOR B XOR Cin, okay, right? But we cannot conclude just by looking at half table. We have to confirm that with the remaining table also. Now, let us look at this combination. Now, this combination is same as this combination, okay, right? And now here what we are doing, okay, now what we are doing, here we have all ones. Now, if we look at this part, everywhere the A value is 1, right? So, now we need to consider what about 1 XOR with result. So, for that again let us go back to the previous slide, okay. So, here what about 1 XOR with some value. For example, in this case 1 XOR 0 is giving 1, okay, 1 XOR we have discussed that this is nothing but XOR, correct. So, 1 XOR 0 is giving 1. Next, 1 XOR 1 is giving 0, means the value is getting complemented, okay, the value is getting complemented, right. Now, let us see whether the same complement is happening in this table or not, okay. We have seen that, okay, we have seen that this part and this part is the same, right. Now, let us observe this part. This part, okay, is complement, okay, if you take complement of all these, are we getting this? For 0 complement 1, 1 complement 0, 1 complement 0, 0 complement 1, are we getting? Yes, we are getting, okay. So, we can conclude that sum is nothing but A XOR B XOR Cin. Earlier we have got that indication from this table. The same was also valid to this, means we have covered this entire part of the table, first 4 columns, right, and that is all we need to consider. We do not need to consider carry, because carry is an output, okay. When it comes to designing logic circuits, output we will consider depending on the inputs, okay. So, sum depending on A, B, Cin, we have considered all possibilities and we have identified that sum is nothing but A XOR B XOR Cin. So, that we could see from the table and we could identify. What about carry? Now, if we see carry, just by looking at this table, okay, we are not able to identify which is the single gates or, okay. Now, for example, 3 input XOR gate will perform sum according to the previous discussion that we just had, but carry we cannot look at this and identify. We need some simplification, like some school problems, very simple problem, you can see the question, you can tell the answer. But if the problem is complicated, you need to take pen and paper, you need to analyze and get the result. Okay. Now for such analysis, we will make use of Karnaugh maps or K-maps. So why do we need K-map? To simplify the Boolean algebra. Okay. To keep it simple, now the expression that we got, that is sum. Sum we got A XOR B XOR Cn. This is a Boolean expression. Okay. This is a Boolean expression. Example of a Boolean expression. It is simply, you can call it as a formula in the Boolean domain. Next, now what is this K-map technique? Okay, you will draw some boxes. Okay, what each box represents, it represents a min term in sum of products form. Okay, in sum of products form. Okay, right, there are different versions also. One version that we need for analyzing the full adder, that one only we will study in this class. Next, another key point is the adjacent squares differ by one variable. Okay, all this we will see that map, then you can understand. Then K-map can be viewed as reorganized version of the truth table. Truth table you rearrange, okay, in a different way, then it is the K-map. Let us look at K-map and let us see how these points, okay, form the basis for the K-map. So now here what are all the points? Okay, if you see these, let us look at this 0 0, okay, then 0 1. The first 0 is remaining same. Okay, the first 0 is remaining same, but the second digit is not the same, right? Only one bit change. Okay, so differ by one variable, right? Adjacent squares differ by one variable. Okay, now let's compare any two. It is not that 1 1 is changing to 0 0. No, 1 1 is changing to 1 0. So there is only one bit change. Okay, you analyze anywhere, any two adjacent boxes, they have only one bit change. Okay, then let us look at all the points. Collection, so to simplify Boolean algebra, we will simplify and we will check. Collection of square boxes, second point. Okay, collection of square boxes, yes, collection of square boxes. Okay, so many boxes we have, fine. Next, each box represents a min term. Okay, right. So here, for example, if you take this particular box, we can represent this box value as A bar, B bar, C bar. How? Here if you see corresponding to A, we have a 0, means A in its complementary form. Corresponding to B, we have a 0. Okay, so B is in its complementary form. Again corresponding to C, we have a 0, means C is in complementary form. So this box represents A bar, B bar, C bar. Likewise, let us take this box. Okay, this box represents all are 1. So all in true form, A, B, C. All are in the true form. Okay, so that is what is mentioned here. That is, represents a min term. This is one min term. Okay, A bar, B bar, C bar together, this is another min term. What is the meaning of this one? Means, it means A into B into C. What is the meaning of this? It means A bar into B bar into C bar. Okay, now let us see why it is called as min term. That is, ABC, if you see ABC, the possible values can be 0 or 1. A can take value 0, A can take value 1. Likewise with BC. Okay, now when you multiply any value with 0, you are going to get 0. So this product will give you the minimum of the 3. Hence this term is called as minterm. Okay, hence this term is called as minterm. Means if any one of A, B and C is 0, suppose A is 0, then result is 0. Okay, suppose B is 0, A, C both are 1, again the result is 0. So it is giving the minimum of the 3 values, hence this term is called as minterm. Okay, so we have studied minterm. Then what is this SOP? SOP we have just seen. Okay, it is sum of product, sum of products. Okay, product is multiplication, sum of products is, okay, addition of products, right? So we will see the final expression, we will see how we can simplify this, okay, KMap, and then we will get an expression, then we will see why it is sum of products. Okay. So first, now let us use KMap to simplify this. So we are going to see 4 columns. What are the 4 columns? A, B, C, N, carry out. Only these 4, sum already we have simplified. Okay, so we are not going to see that. We are only going to see A, B, C, N and carry. So here, where all we have ones, where all we have zeros, we need to note down in the table. Okay, alright. So let us see where all we have ones. So where all we have ones, this position we have 1. Okay, so what is that position? A is 0, B is 1, C is 1. So where A is 0, B is 1, C is 1, here we need to put a 1. Okay, we have written a 1 there. Next, likewise remaining where all we have ones, remaining this one, this one, this one, 3 places we have ones. What are the 3 places? 101, 110, 111. Okay, 101, okay, 110, 110 here. Next 1, 1, 1 here. All 3 places we are going to put ones. Okay, so that is the first step, right? So obviously rest all you can put zeros, 4 zeros, 4 ones. This is what the table consists of. Okay, the table consisting of 1, 2, 3, 4, 4 zeros, 4 ones that we have written in this manner. Okay, so that is the reason here it is mentioned KMap can be viewed as a reorganized version of the truth table. Okay, fine. So reorganized version of the truth table. Now what we need to do is we need to go for mapping. Suppose we had all the boxes 1, then we could map like this entire, but all are not ones. So all 8 mapping is not possible. So first you will check whether all 8 mapping is there possible. No, it's not possible. 4 ones, is it possible? Suppose if you had a 1 here, suppose if this was a 1, then 4 ones was possible, but that is not the case. Okay, 4 ones is also not possible. Suppose you had a 1 here, then 4 ones would have been possible, but that is not the case. So by looking at it, I see that 4 ones are not possible. Then next we have to go for whether can we map 2 to 1s together. Yes, we can map. For example, this is one map. Okay, and this is another map. This is another map. Okay, now this one has been mapped 3 times. It's okay. It's okay. It can be mapped multiple number of times. Fine. But we have to find possible pairs. If the pair is possible, we have to make a pair. This is the process for KMap. So now we have to write the expressions. So first if you see what is common in these 2. What is common in these 2? Okay. This, okay, only this is common, right? One column, same column, so only this one is common. So both B and C are in its true form. So what will be the expression for this? The expression for that will be BC. Okay, right? Next, we have already completed BC. Next let us check this one. Okay, so here along the row is common. Fine. Now we have to check the column. This second one is common. Okay, so first one corresponds to A, this second one here corresponds to C. Fine. So we can take that as AC. Okay. So we have completed BC, we have completed AC. Next let us look at this last one. Here again this A is common. Okay, and in these two we have to check these two. What is common? This first one is common. Okay, the first one is common. So this corresponds to A and the first one corresponds to B. So the expression we will get is AB. Now we have to add these together. Now if you see, this is a product A into C. It's a product. Okay, right? Then plus is nothing but sum. Okay, plus is nothing but sum. Hence this form is sum of product, SOP, and that is what is mentioned here. Okay, sum of products form. Fine. So now let us develop the circuit diagram for this. Expression of sum we got A XOR B XOR Cn. Carry expression we got AB plus BC plus AC. Okay, so sum will be A XOR B XOR Cn. Simply we are taking one 3 input XOR gate. Okay, to implement AB, A into B. Okay, multiplication A into B is implemented by AND gate. Right, the plus which is the addition. Okay, the plus is implemented by OR gate. In Boolean algebra, plus is implemented by OR gate, and multiplication, okay, plus is implemented by OR gate, multiplication is implemented by AND gate. Okay, plus is implemented by OR, multiplication by AND. So first, if you look at this A into B, we need to use the AND gate. So for A into B here, AND gate. Next, B into C, AND gate. So we are taking input from this one. Okay, we are taking B and then we are taking Cn. Okay, B into Cn, another AND gate. Next, one more, A into C. Okay, so for again A into C, another AND gate, right? And then next we have plus in between. Okay, we have plus in between, right? So 3 inputs. So we need to take 3 input OR gate. Join all this together. This is the circuit for full adder. What do I mean by this is the circuit for full adder? Means you give inputs here. This circuit is going to perform full addition. It is going to give the outputs here. So in summary, we have seen what is half adder. Okay, it is simply addition of 2 bits without carry. Full addition is addition of 3 bits. What is the third bit? Carry from previous stage. Okay, right? Next, we have seen KMap to simplify Boolean expression. And where do you need adders? Okay, in digital systems, right? Processors, calculators, you need the adders. Okay, fine. So this is about half adder, full adder, and the role of KMap to simplify and get the minimized expressions. And we have also seen the applications. We have seen, okay, the disadvantages of half adder, why we need full adder. Okay, right? So that's all for today's class. Thank you so much.